Hi, students. In this lecture, I am going to discuss problems. Let us see first one. Let's see the question given. A uniform sphere of mass m and radius r starts rolling without slipping down an inclined plane. Find the time dependence of the change in angular momentum of the sphere relative to the point of contact at the initial moment if surface is rough, if surface is smooth. Let us see how to calculate. So first make a diagram for the given data. A uniform sphere starts rolling without slipping down an inclined plane. Suppose the angle is a theta, angle of inclination. Now sphere rolls down without slipping. So this is a possible if there is sufficient friction between the sphere and inclined plane. Right. Now see what happens rolling without slipping. Suppose velocity is now V naught. Then omega will be, means this is velocity at one instant. At that instant, omega value will be, it is V naught by R. That is omega value. So these values will change continuously. Okay. Right. Now we have to focus on find the time dependence of the angular momentum of the sphere relative to the point of contact at the initial moment. Suppose this is now the initial position of the sphere. This is now contact point about which we want to calculate change in angular momentum. So initially sphere was at this location. Now sphere keep on moving down. It rolls down the incline. About this point, we have to calculate change in angular momentum. Right. So one thing we have to focus on the sphere, net force is not zero because when body rolls down the incline, it rolls down with a constant acceleration, which is equal to g sine theta upon 1 plus beta. This is what we have learned in earlier lectures, right? So since net force is not zero, net torque is not same about any point. If you are changing point, torque also changes. That means even angular momentum changes if you are changing the point. That's why it is mentioned here about the contact point. Now see what happens about the contact point. See number of forces that are acting. EMG downwards, normal reaction through center, normal to incline, and frictional force up the incline. So I'm making diagram separately. On the sphere, number of forces that are acting. This is now inclined plane. Now focus of forces that are acting. EMG, or I can take two components for MG parallel to incline. EMG is sine theta. Normal to incline, it is mg cos theta. Normal reaction, that is a passing through center of mass. Next, coming to frictional force at the contact, that will be up the incline. So we have learned that whether body rolls down the incline or up the incline, in both the cases, frictional force on the body will be up the incline. Okay. So now we are taking change in angular momentum about the contact point. Okay. So here what I am doing is, we have learned that net torque is equal to net torque is equal to rate of change of angular momentum with respect to time. Okay. So from this we can write change in angular momentum in a small time interval is given by that net torque into dt, right? So if you want to change, we have to integrate. Okay. Now focus carefully in this one about the contact point. Normal reaction passing through contact point. So by normal reaction, no torque. By friction also no torque. By this weight component, mg cos theta, no torque. Now torque is only because of mg sin theta. Okay. So it is now mg sin theta into r. It is a constant. That means I can write here change in angular momentum, that is equal to, focus the modulus value, net torque equal to, since it is now constant, I am taking now the torque outside, that is mg sin theta, mg sin theta into r. This is now net torque on the body about the contact point. Integration of dt, that gives us t. So input t, right? This is now change in angular momentum as a function of time about the contact point, right? For example, if you are taking about center of mass, then see what is net torque because of mg. There is no torque, right? Because of normal reaction, there is no torque. Now torque will be only because of static friction, right? And we have learned that this static friction is equal to beta by 1 plus beta into, I am writing here, Fs equal to beta upon 1 plus beta into mg sin theta, right? If you are taking torque about center of mass, torque about center of mass, then see what happens. This value into R, right? That means torque has changed. Here mg sin theta into R, that is a torque into T. Here beta by 1 plus beta into mg sin theta into R, that is a torque into T. So here what I'm saying is, since net force on the body is not zero, net torque on the body is depending on about which point we are calculating. So here we have to focus very carefully. We are focusing on about the contact point. So this is the answer. If you are focusing about center of mass, then answer will be delta L equal to modulus value, this Fs into R, that is a torque, into T, right? So like this, we have to focus about which point we are calculating. Next, in this one more condition given that if the surface is smooth, now see what happens. Since we are taking about the contact point, whether surface is smooth or rough, no change in torque, right? I am repeating. Since we are taking about the contact point, because of friction, torque is zero. That means whether it is a rough surface or smooth surface, there is no change in the net torque. because it remains same, mg sine theta into r. That means change in angular momentum about the contact point does not change, whether it is a rough inclined plane or smooth inclined plane. But we have to focus where change comes. If friction is sufficient, body continues to roll without slipping. But if it is a smooth surface, initially this is V naught, this is V naught by R. But when it is a smooth one, there is no torque about center of mass. If you are taking a smooth one, about center of mass, there is no torque. That means throughout the motion, omega value does not change. But coming to VCM, that will change. That means if it is a smooth inclined plane, it moves down with rolling, but it rolls with slipping. That is the only change. In the answer, there is no change. Okay. So I hope you got the clarity. Let us see next question. As solid sphere rolls down a parabolic path A, B, C from a height h as shown, portion AB of the path is rough. AB is rough, but coming to BC, it is smooth. Find the height reached by the ball on BC. Okay. See now carefully how to start. AB rough, BC smooth. See diagram given. This is AB, remaining part BC. AB is rough. It is rough and BC is smooth. Okay. Height is given H. Height is H. So condition is that it is rolling without slipping. So when it rolls without slipping, there is no energy loss. That means a loss in the gravitational potential energy is mgh, which converts completely into kinetic energy because of rolling motion. Okay. That means now kinetic energy at the bottom, it is equal to mgh. Now focus carefully. This is equal to half m bc square, where bc is speed of center of mass into 1 plus beta, right? Now in this first part, half m bc square into 1, that is a kinetic energy because of translation. Next part, half m bc square into beta, that is a kinetic energy because of rotation. See what is a kinetic energy because of rotation? It is equal to, because of rotation kinetic energy is 2 by 7 mgh. See carefully. I want to calculate half m bc square into beta value. This total value is half m bc square into 1 plus 2 by 5, that is 7 by 5, right? I am writing here ratio rotational kinetic energy to translation kinetic energy. See ratio rotation, it is beta, translation, it is only 1. See carefully. Half m bc square into 1 translation, half m bc square into beta rotation. So beta by 1. Beta value 2 by 5, right? So here out of, see 2 plus 5, 7. Out of 7 parts, 2 parts will be rotation, 5 parts will be translation. Okay. So because of translation, it is 5 upon 7 mgh. So now you should be very careful here. Since BC is given smooth, there is no change in angular velocity. There is no change in angular velocity from B to C. That means there is no change in kinetic energy because of rotation. This is nothing but a half 5 omega square. Omega does not change from B to C because it is a smooth surface. That means kinetic energy because of rotation does not change. After reaching some height, still it is having same omega, no change in that. The only thing is kinetic energy because of a translation becomes a zero. Therefore, this loss converts into gain in the gravitational potential energy. I'm writing here loss in the kinetic energy because of translation converts into gravitational potential energy. Suppose a height equal to h dash. So raise in the gravitational potential energy mgh dash, that is nothing but loss of kinetic energy because of translation, which is equal to 5 upon 7 mgh. mg cancels, h dash is equal to 5 upon 7 into h. Okay. So you have to keep in mind that there is no change in the kinetic energy because of rotation. Therefore, only change is now this is converting into potential energy. If you get that clarity, it is very simple. Okay. Let us see next problem. Let's see the question given. A hemisphere of radius r and mass capital pulled by means of a string as shown so that it moves with a uniform velocity. Condition given, it is uniform velocity. It means the body is in equilibrium. So uniform velocity means net force zero, right? Here there is no rotation, means there is no torque. So net force zero, net torque also zero. If mu is the coefficient of friction with the surface, find the angle of inclination of the hemisphere. Okay. And a hint is given. Center of gravity of hemisphere lies at a distance 3r by 8 from the base. From the base means this is now base. Okay. From the base distance equal to 3r by 8. Let us see how to find this theta value. Right. First make the diagram given. Right. Let us see now diagram given. It is now given hemisphere. Hemisphere. Force F is applied horizontally. Now this makes an angle theta. Let us take do one thing, make diagram 1 second. Right. Let us take first of all, let us take this is the base. With this base, that force makes an angle theta. Force makes an angle theta. It makes angle theta. This force is now F. This is now hemisphere. Let us draw hemisphere now. Right. This is now hemisphere. Suppose this is now center, that is O. So first of all, focus here. How many forces are acting on the object? Right. Now see carefully. Coming to here, I'm taking one normal at the contact. Normal reaction is now normal to contact. It is like this. Normal reaction. Friction at the contact. In fact, if you observe, only one point will be in contact with the ground. Friction is now like this. It is now slipping. Friction will be kinetic. That is mu k into normal reaction. Okay. Next, let us draw normal for this base. Normal. And you can take here mg. Mg will be passing through center of mass, or you can say center of gravity of the hemisphere. And center of gravity is now at a distance 3r by 8. Okay. We can take somewhere here center of gravity mg vertically downwards. First condition given that it is having constant velocity. That means net force is zero. Net force is zero. Net torque also zero. It has only translation, no rotation. Since net torque zero, sorry, net force zero, net torque will be same about any point. Okay. So here what I'm doing is I'm taking out torque equation about contact point. You can see it is about contact point. Then see what happens. Because of normal reaction and because of friction, torque becomes zero. That is the advantage of taking torque equation about contact point. If you remember, while discussing equilibrium of rigid body, there I have discussed that whenever we are taking torque equation, if net force zero, net torque will be same about any point. In that case, we are choosing a point through which more number of forces are passing. That makes a calculation more simple. Okay. Now, in this case, through contact point, more number of forces are passing. That's why taking here about contact point. Okay. Then about contact point, because of applied force, torque will be clockwise. And because of gravity, torque will be anti-clockwise. You should be very careful. The sense of rotation. Okay. About the contact point, due to applied force, it will be clockwise. Because of gravity about the contact point, it is anti-clockwise. Now see what figure about contact point because of F. It is F into. You can see here, this is now R. This will be R sine theta. This length is R sine theta. Remaining is now R minus R sine theta. So F into R minus R sine theta. So force into perpendicular distance. Okay. Right. That is equal to mg into. Now focus carefully here. Between these two lines separation. So we can see now this length how much. We can see This angle also same. This is also theta. Suppose this is now C. We are knowing that OC value 3R by 8. That is given OC value 3R by 8. Okay. It is 3R by 8. Then here OC becomes in this triangle, OC becomes hypotenuse and this becomes now opposite side. So this becomes now 3R by 8 into sine theta. It is 3R by 8 into sine theta. So if you are able to write this equation, remaining just calculation part. So from this, sine theta is equal to 8 mu upon 3 plus 8 mu. That is a final answer. So here key point is that the body is in equilibrium. So net force 0 and net torque is 0. Okay.